Okay, we're starting. We're going to continue with limits today. Lots more to talk about limits. Oh, by the way, the review and the solutions to the review, they're already posted online, so hopefully you all have seen that. And you've all already started trying to do it. So that's kind of a good prep. It kind of shows what I think is important to know at this point. So I also think I gave you guys a guideline for how I think you should be studying, because I know that some students have this habit of studying from their homework and rereading the textbook, but really time-wise that's not very efficient. I mean, if you actually went through the homework properly the first time, you shouldn't have to do that again. So it's more now where you're trying to focus on what you think is be important to test you on. Because the homework is kind of geared towards giving you this overall general understanding, but on the test I'm testing you for specific skills that I can measure very well. And so it's nice to actually practice directly for what you're going to be training for. So you should actually take that review seriously, and it's better to actually go through the review than it is to actually even go over your homework. To just really understand and use that to gauge where you are in terms of what your understanding is. But we are going to continue with 2.2. Never really gave you anything concrete yet, but we were just playing around with some stuff. We looked at what a limit was, and we looked at some examples of finding them. I also introduced, I believe, limits at infinity and infinite limits to you guys. Did we talk about a guy like this? So let's just jump into some more examples here. Can we talk about a guy like that? I don't think we would. Let's look at these three here. Because they'll illustrate another very important level of analysis that we're going to be looking at. We can also talk about this guy. Which they almost seem to be the same thing, but they're actually different. So in the first example I gave you guys with limits, it was actually a very nice function. I just asked you, what is the limit as x approaches 1 of x plus 1? X plus 1 was a nice function. You could literally actually just plug in 1 and get an answer. And that's pretty much telling you the closest y value, because you can literally be at the point. In the second example, we looked at x squared minus 1 divided by x minus 1. Of course, in that case, you couldn't actually plug in x equals 1. That was a little bit more tricky. But knowing our algebra and knowing how to simplify, we could avoid that part. Okay? But now you look at an example like this, and you see that neither of those options are available to you. You can't really plug in the number because you can't plug in 0, you can't divide by 0. But at the same time, you can't really simplify to actually get rid of that 0 in the denominator. There's nothing to factor and cancel that guy in the bottom. Okay? So how do you think of approaching a guy like this? Ideas? Yeah?
You could plug in numbers that are closer and closer to 0, so you do 0.01,
Sure.
0.001.
So one option is to actually do that whole strategy where we're actually plugging in values and then seeing what the 1 over x is going towards as we approach this value 0, which we know we cannot actually obtain a value for. So in one sense, you can start to plug in some really easy values that you can really see what 1 over x is right away. So something inching closer and closer to 0, say from the positive side. So maybe like 0.1 or 1/10. What if x is 1/10 of a unit away from 0? What would 1 over x be? It would be 10. Okay, so you go inch a little closer. 0.01, 100. What would the 1 over x be? 100. Right? Or you go to 1 over 1,000. What's that guy going to be? Well, it's going to be 1,000. Okay? What if you get super close to 0? 1 over a billion. What's this guy going to be? It's going to be a billion. And you can kind of see a pattern here. Hopefully you see a pattern. Well, what if we go the other way? What if we plug in, say, minus 1 over 10? So we get minus 10. Plug in minus 1 over 100. See minus 100. Plug in minus 1 over 1,000. We'll see minus 1,000. And so on and so forth. Plug in minus 1 over 1 with a lot of zeros behind it. You'll get minus that of 1 with all those 1, 2, 3, 4, 5, 6, 7, 1, 2, 4, 5, 6, 7, 8. So what's the pattern that you're seeing coming from this side? What's happening to all these numbers? They're getting larger but more and more negative, right? So they actually going down. And they seem to be going down without bound. It kind of seems like these numbers are tending towards, and you can see that it doesn't seem like it will stop. If I divide 1 by even a larger number, the response over here is going to be even a larger number. So it doesn't seem that it's going to slow down or settle anywhere. So you're kind of thinking that this is going towards minus infinity. It's going to keep getting more and more negative, keep getting larger and larger. Conversely, if you come from the positive side, you see a similar behavior happening. The difference is the numbers are all positive, but they also seem to be growing without bound, so you can kind of see that. Right? Now, there's another way you can have thought about this. Let's say you were paying attention to my quizzes and stuff, and I've actually asked you to graph this function several times, and I mentioned that knowing its graph is important. So let's say we actually knew the graph in our heads. We see a picture in our heads when we look at 1 over x. Hopefully we all know by this point that it looks like this. Notice that the picture can tell you all this information that was happening in the table, but it can tell you kind of like that. You can kind of look at the picture and kind of see the behavior that's happening. So here's our 0. Obviously we can't actually touch 0, that's why it's an asymptote. But you'll notice that as you're inching closer to 0, your y values are getting bigger and bigger and bigger and bigger and bigger. Right? You can see as you're inching towards it this way, the y values keep getting larger and larger that way. So we can see from the picture that this behavior is happening. And what does this mean? X approaches 0 with a plus. It means from the right. So looking at this picture and examining from the right, if I'm approaching 0 from the positive side, my y values are going bigger and bigger. Remember, that's what the limit was. The limit is us tracking the y value. Remember, that was what the limit is. When your x is getting close to something, what is happening to the y value? That is your limit. So as we're getting close to 0 from the right, our y values seem to be getting bigger and bigger and bigger. And so we can capture that behavior by just saying, you know what, this is positive infinity. And there are 2 ways we could have come to that conclusion. We can do a table, and we can do a graph. And it's worth noting that the first 2 strategies that I showed you from the first 2 examples don't apply here. I can't plug in the number, and I can't simplify to plug in the number. So I have to do something else. The picture is a great way to actually do it. You could also do a table of values. Completely valid, but not exactly an efficient way to do things, especially if my function was a lot more complicated than 1 over something, where I know I can just flip the answers. Okay? In a similar way, if I'm approaching 0 from the left side, I'll notice that my y values, the closer I get to 0, my y values are getting smaller and smaller and smaller, and they keep going down. So it seems that from the left side, it will go to negative infinity. And we can get that also from the table. Given that, what would you say the limit as x approaches 0 of 1 over x is? Does not exist. Right? Now, clearly these limits aren't really numbers, but the fact is, we kind of give them an answer, so they're kind of defined in some sense, even though they're undefined. We will take infinity or negative infinity as a definition, because it's important to talk about the behavior of functions. And it's an important thing to understand what's going on with the behavior, and we'll actually use this idea. So that's why I don't want you to think of these as undefined. Think of it as being an infinite limit. right? However, the infinities are different. One is positive infinity, one is negative infinity. They're literally going in the opposite directions, and it doesn't have a consistent behavior. And so from the left and right, they disagree, and so the entire limit is actually, it does not exist. Contrast that with the function 1 over x squared. What do you think I can say is the limit there? So we literally just covered A, B, and C from that example. What do you think about this guy? Yeah?
Would the limit be infinite since like the negative number will become positive, so both will be infinite, like left and right?
Sure. Remember what the picture looks like here as well?
It would be like 2.
Right. The picture of 1 over x squared looks like that. In fact, the picture of 1 over x to a power where that power is even will all look like this. It's just the steepness that will change. Whereas if you have 1 over x to an odd power, they'll all kind of look like that. So it's just a matter of the steepness that's changed. So here we can kind of look at the same sort of idea. If we're approaching 0 from the right side, our graphs are going up and up and up. If we're approaching 0 from the left side, the graph is going up and up and up. So it tells me that my y is approaching positive infinity from the left. My y is also approaching positive infinity if I come from the right. These guys, though they're not numbers, they are in agreement. They're both infinite and they're both positive infinites. So I can say that the answer to this is positive infinity. So not necessarily an answer, but it definitely can talk about the behavior of this function. And clearly the fact that this is infinity and not a specific number also kind of hints towards the fact that it's actually not defined here. So it's not going to trick you into thinking the function makes sense when it doesn't. So that's how you do such a limit. Let's look at another. Or maybe I can just go into the properties. Let me tell you about his strategy first. Yeah, strategy will apply even if I haven't told you what I plan on telling you. Strategy for approaching limits. So limits might be a little fuzzy idea to some of you guys, so I want to give you some sort of concrete footing to approach this thing. So to find the limit as x approaches a of some function. Now, in a different kind of math class, this process will be even longer, but in this class, here are the kind of things that you want to look for. Right? Because if I give you limits on an exam, I'm not going to tell you what to do. I'm not going to tell you, oh, you should probably use a table of values here, or oh, you should probably think of simplifying. I'm just going to give you a limit and you have to figure out what you have to do. Okay? So here's how you basically want to approach a limit problem. I give you a random limit problem. It shows up on a test, oh, find the limit of this. Right? What's the first thing that you look for? Well, you kind of go in order of what would be easiest to do. So the first thing is you check is you try to plug in it's literally the first thing you'll do with any limit. Right? So in that actually worked with our first example. So you try to plug in the number, and if you can plug in the number, if possible, the y value you get is the limit. So if you can plug in that number that your x is approaching into the function, like that example where we had x approaching 1 of x plus 1, you plug in 1, the output is 2, that's your limit. So that's the first case. Such a function where something like that would work is called a continuous function, and I will define what a continuous function is for you later. But it's literally one of the first things you will think of doing. Okay? Here's a random limit. The first thing I'm going to try to do is plug in the number. It's not always possible, that's why it's only step 1, because I couldn't have done that here. But that's the first thing you'll always try to do, is the first thing you will look for when faced with a random limit. So if that doesn't work, so if not, you move on to step 2. Now in step 2, what you're going to do is try to simplify it to be able to plug in the limit. Possible, then this output is your limit. Okay? So you'll notice that if you look at our second example, the limit as x approaches 1 of x squared minus 1 over x minus 1, strategy 2 is the strategy that worked. Because I noticed that I couldn't actually plug in x, but I realized that the top could simplify and cancel the denominator, and so the denominator wouldn't be a problem anymore, and then I could plug in x. The fact that the function isn't defined there is irrelevant compared to the limit, and so that actually gave you the answer. That told you where the y value was heading. Right? So given a random limit, the first thing I'm going to try to do, plug in the x value. If not possible, try to simplify to plug in the x value. This is where your algebra skills come in. You have to know how to factor and do all that stuff that we were talking about in the beginning of class 3. So we're in a situation where if we plug in, so if not, then you move to the next step. So now you find yourself in a situation where if you plug in, you can't get the answer that way. And even if you simplify, it probably can't be simplified, or even if you simplify, it doesn't get rid of the problem. Then you find yourself in the third stage. And in this third stage, what do you think we would do? Well, we kind of did an example of that, right? The 1 over x as x approaches 0 was such an example. In the third stage, you will at this point, you can't really plug in, you can't really simplify. So then you have to somehow figure out how the y value is behaving otherwise. One of the easiest ways is to actually use a table of values or its graph. By the way, using its graph, this is by far the recommended course of action. So of course you have to know what the graphs of some of these common functions would look like. Okay. It will be the quickest way. It'll be a lot quicker in general than you plugging in a bunch of numbers and checking. And even if you have a calculator with you, that can become quite annoying with even a moderately complicated function. Okay. So, but if you know what the picture would look like and you have some idea of what the picture is doing, that can actually tell you what the y value is doing, and so you can get away with a lot. 4. well, this is kind of continuation of 3. And this is really about knowing the behavior of functions in relation to each other. So you might be faced with a problem where you have different kinds of functions being grouped together, and you kind of want to figure out what's going on with them. There's one common relationship, kind of relationship, and this strategy here can extend to other things, but common application of 4 is when finding limits at infinity. So I'm actually going to give you the relationships, how certain functions relate to each other. This is something we could prove, but we're not going to prove it in this class. But we do know now, because I'm going to tell you, how certain functions behave as you're going off to infinity. So, by the way, you never get to infinity, but we're approaching infinity. And what are the common functions that we've seen in this class so far? We've seen polynomials, or power functions. We've seen logs. We've seen exponentials. There are also functions that are very common in calculus called factorials. We won't do a lot with factorials here. There are also variable exponentials. Now these guys all have relative sizes as you're going off to infinity. Some of them are a lot bigger than others. So here's the relationship. The basic one is the log function. As x approaches infinity. If you look at a log function, it is a lot smaller, comparatively speaking, to a polynomial. Meaning, if your x is going off to infinity, and you want to compare the relative sizes of a polynomial compared to a logarithmic function, the polynomial will be bigger, right? And this symbol here means it will be very bigger, if that's a term. To the point where eventually off to in infinity, this guy will be so big, it's almost like that guy's nothing. It's that they can get that much bigger, right? So it's like this guy might as well be 0 compared to this guy if you're off to infinity, right? There's what's bigger than this guy, from what we've been studying, as I might have mentioned, is an exponential function. So something like a. So like e to the x, where of course here a is greater than 1. And any such function will be bigger than any polynomial. It will also be bigger than any log function. Right? And the base almost doesn't matter. But we're using a greater than 1. Now these kinds of functions we haven't really seen in this class, so I just like to tell people for completeness. There's something called x factorial. and there's something like x to the x. So it's kind of like an exponential, except the base is also a variable. We are going to look at functions like these, but not. You probably don't need to know these very well, but that's true in case it ever comes up in your life. But these you need to know, right? The relative sizes of these guys. So how can you use that to help you with a limit? So for example, let's say you're taking the limit as x approaches infinity of x to the fifth divided by e to the x. Let's look at that kind of thing. So you're faced with that random limit. The first idea you would have is to plug in, right? So you can't really plug in infinity, but you'll kind of think of it as plugging in infinity. But what would the top be? Well, that would be infinity. And what would the bottom be? That would be infinity. And you're kind of not sure who's beating who. So that step one didn't help you, but then you move on to step two and you're like, okay, let's try and simplify. There's nothing to simplify here. So that doesn't help you, right? And then you jump to the third step and you're like, okay, what would the graph of this look like? Drawing the graph of that is going to be very complicated. Even after I teach you guys curve sketching, which we will do later in the semester, graphing something like that is going to be a complicated thing to do by hand, right? And you don't have a graphing calculator accessible. So then that leaves you with option 4, and just knowing about how these functions behave in relation to each other. And you would realize that an exponential is going to be bigger than any polynomial. It doesn't matter what the power of the polynomial is. It didn't even have to be x to the fifth. I could have an x to the million. The result is not going to be any different, right? Exponentials are huge compared to polynomials when you're going at infinity. It does not matter what the power is, right? So just knowing about that relationship between an exponential and a polynomial is going to help you. Because now what you're going to look at, when you see this, what you're seeing now is you're seeing this guy as really small and that guy as really huge. And you kind of think, what happens to a fraction if the numerator is very small and tiny and the denominator is huge? What kind of number would that approach? Yeah.
0.
It would approach 0. Right? You think of any fraction, right? 1 over 10 compared to 1 over 1,000, compared to 1 over 1,000,000, compared to 1 over 1,000,000,000. What's happening to the fraction? They're all getting smaller. The larger the denominator is in relation to the numerator, the smaller the fraction is. Right? So you see this, you immediately kind of know that the answer is 0. And the way you know that is knowing that an exponential and a polynomial, the exponential is always going to win. And it doesn't matter what the polynomial is doing or how big the polynomial's power is, it's always going to win. Also, it doesn't matter about the log, what base it's in, the polynomial is always going to beat the log. They rise, this guy increases very slowly compared to this guy, and this guy increases very slowly compared to that guy. And just knowing that relationship, you can help gauge things. Also, it would help you to know that if you're doing this, and it was the other way around, like e to the x over x to 1,000,000, the same idea would apply. Now you'll see a fraction where the numerator is huge and the denominator is small. And that kind of tells you, well, that would go to infinity, right? Because that's what happened to a fraction. When the numerator is huge and the denominator is small, the fraction gets bigger and bigger and bigger. So those are some ideas that you can use, apply to approaching limit problems. And essentially the order in which I gave you these steps is always the order in which you want to approach them. So I give you a random limit problem, I don't give you any information, I just say, do this limit problem. The first thing you're going to look for is, can I plug in the number, right? Because if you can plug in the number, that's easy. Just plug in the number and compute it, and that's your answer. That's the easiest thing to actually see, right? So you can I plug in the number? If you can't plug in the number right away, then you check. Could I simplify to plug in the number? Can I factor things and cancel things? Or can I reorder things in such a way that I can plug in the number, right? Simplify this guy. And if that doesn't work, the next thing you're going to try to do is, well, the whole point of a limit is figuring out what happens to the y value, so I can kind of figure that out by knowing what the graph is doing. So then you kind of think about the graph, right, and what it's doing, right? But then there are going to be cases when we're mixing and matching functions, and while you might know what a polynomial by itself looks like, or an exponential by itself looks like, knowing what the division of those look like is actually a very challenging thing to know. So in this case, you wouldn't be able to really look at the graph, but just knowing how these functions relate to each other, that can help you, especially if you're going to infinity. It turns out if you're not going to infinity on something like this, you could literally just plug in the number, right? Like if you had to do like limit as x approaches 0 of x to the 5th over e to the x, you can literally just plug in 0 here. Because e to the 0 is 1, that's just 0 over 1, the answer is 0, right? So if you have two of these different functions, you can literally just use step 1 and get to it a lot of the times. But in the case where you're going to infinite limits, knowing this relationship is actually very beneficial. And so that would be kind of the last step in your analysis. There are also a lot of situations where the answer is kind of known to us as well. And I will do those examples. Like there are shortcuts for like rational functions and things like that. But I want to actually tell you about some more properties of limits before we continue. But in general, based on the examples and playing around with things, this is kind of the approach I want you to take towards limit problems. Don't forget the goal. The goal is to try to figure out what the y value is doing when the x value is doing something. And it's also in the context of, I don't care about being at a point, I just care about getting close to a point. Okay, so this whole approaching idea is a very important idea. And also the idea is, I just want to figure out what the y value is doing. That's the idea. That's what you want to get through your heads. And the strategy I just gave you is just a strategy to facilitate coming away with that knowledge. There are many uses of limits, but we'll see probably the most important one in calculus pretty soon in the next section of chapter 2. But for now, that's kind of what I want you to. I want you to be able to actually just compute. And just like exponentials and logarithms, there are laws with limits. Or let's call them the limit laws. So let C be a constant. And let limit as x approaches a of f of x equals L. Limit as x approaches a of g of x equals n. Where these limits exist and are finite. So pretend C is some constant, and these are just two limits where we have an answer, and the answer is not infinite. Then the following rules apply to limits. 1. The limit as x approaches a of a constant times a function is going to be equal to the constant times the limit of the function. In other words, this case it will be c times l. Right? So this is a property that we can do with limits. You can factor constants out and it will not actually change the answer. So example, if I'm thinking of the limit as x approaches 1 of 2x plus 2, it's a very silly example, but I just want you to get the idea. 2 is a constant, that's a common factor. I could factor that out. And then I can actually find the limit of this expression, which we actually knew how to do before. But we know that that answer was 2, and then we just multiply that by 2, so this is just 2 times 2, that answer would be 4. Okay? So you can actually factor constants out a limit, and it won't actually change the answer. And you can actually do this in the original way that we do that, draw the graph, and you can track the y values, and you'll realize that the answer is actually also 4. Right? But factoring out a constant from a limit does not change the answer. You can do that as you please, depending on what's easier for you. Right? Constants can factor outside of limits. This is a property. 2. If we're taking the limit of a sum or a difference of functions, then it turns out that that is equal to the sum or the difference of the limits individually. In other words, limits distribute across sums. Okay? Not everything distributes across sums, but limits do. Okay? So if I have, for example, limit as x approaches 1 of x squared plus e to the x, I could think of this as the limit as x approaches 1 of x squared plus the limit as x approaches 1 of e to the x. Here, step 1, plug in. That's just 1 as the answer. Here, step 2, plug in. That's just e as the answer. And that will be the answer here. You can also note we could have used the first strategy that I mentioned. We could have plugged in from the beginning. Right, so if you're faced with the limit as x approaches 1 of x squared plus e to the x, you could right away just plug in 1 squared plus e to the 1 and that's that. But if you are in a situation where it's easier to split it up and deal with one part at a time, know that you can do that and it's still mathematically a valid thing to do. Right? Limits do distribute across sums. So the limit of a sum is just the sum of the limits. By the way, these only apply when the limits are finite. If we have infinities thrown in here, things can get weird. It's not always, the rules won't apply exactly the way that they're applying here. But if you can actually get numerical values towards limits, you can factor constants out, you can split them up over a sum, it will not make a difference. Another thing that limits do is they also distribute across products and divisions. So if you have the limit as x approaches a of f of x times g of x, this is equal to the limit as x approaches a of f of x times the limit as x approaches a of g of x. Right? It's a very weird thing to be able to distribute in this fashion. If you look at the distributive law, it does not work this way, but for limits, this actually works. So if you're looking at something like a limit, let's do another simple silly example of x times e to the x. There's one way you can look at it where you're plugging in, and you just plug in 1 times e to the 1, so the answer is e. The other way you can do is you can apply this rule, and you can just look at this as the limit as x approaches 1 of x times the limit as x approaches 1 of e to the x, and this one will be 1, and this one will be e, and you can get e that way. You'll always get the same answer. So limits can distribute across products. But do recognize that that's weird, that the distributive law doesn't actually work that way. But for limits, that works. They also distribute across divisions. So if you have the limit as x approaches a of f of x divided by g of x, that is actually the limit of f of x divided by the limit of g of x. If, of course, this guy's not 0. I guess one other thing, and then I'll let you guys go. Limits can move inside of powers. So if I have the limit of f of x to a power, this is just the limit of f all raised to that power. So if I have a function to a power, I can just take the limit of the inside and apply the power afterwards. If n is a positive. So in fact, example. And again, it's a silly example, but the limit as x approaches 1 of x squared, I could think of this as the limit as x approaches 1 of x, and then squared. It's going to be the same thing. But for more complicated functions, these might come in handy. For now, we'll stop there. We're still not done with limits. There's a lot more to cover. And we'll also talk about continuity, but we will leave that for, I don't know, Wednesday. Because Tuesday we have the test. Right? So get through that. Yes.
Is the test including 2.1, 2.2?
No. Just look at the review and you'll see exactly what the topics are there. And I mentioned it. And the homework for 2.1 homework, leave it on the desk.
I can tell you that one. All the bonus questions.